Thank you for joining us. My name is Chris Lechner. Support for today's program is made possible by Precast Concrete Manufacturers Association, with members in Texas and Oklahoma. For more information on PCMA and their members, please visit precastcma.org. If you have comments or questions on today's program, please contact us at solutions@precastcma.org. Questions will be answered at the conclusion of the program as time allows. Submit questions anytime using the Q&A button at the bottom of your screen. Illustrated visions of future cities often depict sweeping pedestrian walkways, bikeways, elevated roads, and railways. That is happening now. Precast concrete allows the designer to shape that vision while providing functionality and safety. It provides economy from concept to construction and throughout the life cycle. The objective today is to educate, inform, and inspire. Attendees represent education, municipal, state, and federal agencies, contractors, and of course, engineers. You are we hope to inspire. Providing the inspiration today is Greg Reese. Greg Reese is Senior Technical Advisor for Majeski and Masters. His 36-year career in structural engineering includes design and construction, working primarily for contractors. Greg has completed multiple project designs in non-traditional delivery systems, including value engineering and contractor alternates. Please give your attention to Greg Reese.
Thank you, Chris. Bear with me for a minute while I share my screen. And there we go. And then I'm going to put it on slideshow here. All right. Well, welcome to the PCMA webinar. I've actually kind of rebranded this as Advancing Bridge Construction with Precast. We're going to be talking about a lot of different applications of precast, and a lot of it is not really on what you would consider an advanced bridge. These are everyday structures that are fairly common, but what we're doing is we're using precast more and more to make these more constructible, to facilitate economy, to try and reduce construction schedules. And a lot of the concepts I'm going to be going through are really small refinements of ideas that have already been developed by others, and we're just trying to make them a little better with every project that we go through. Just to give you a little background, I know Chris did a very good job of explaining and introducing me and explaining what my background is. I've spent my whole career really involved in pre-stressed post-tension concrete bridges. And my perspective, I think, is that I've spent the majority of my time working for contractors or as a consultant to contractors. So I've spent most of my experience has been on the construction side. And we've actually designed bridges for precasters, for contractors, various other clients. Outside of your more traditional delivery system. So I've got a little bit different perspective on that, and what that means is that we approach our projects from a constructability first standpoint, and we try and use what we call constructability based design, which I'll be going to over in more detail as we go through this. Moving into our presentation here, precast concrete construction really falls into a category of prefabricated bridge elements and systems. This is a category that AASHTO has designated as a key component of accelerated bridge construction. I like to call it Lego construction because to me, this is real similar to Legos. And if you've ever built Legos with your kids, you dump the box out on the dining room table with the instructions, and hopefully in a matter of hours you've got a Millennium Falcon there on your hands. And precast concrete, it really kind of goes together the same way. I found this nice little picture of a cable-stayed bridge made out of Legos. in that, you know, what it means is, you know, you're bringing pieces to the site that are already made, and you're assembling them on site in a more rapid fashion to really create complex structures. And as I go through this, I'm going to be talking really from project experiences, and I've tried to focus the majority of that on projects that we worked on in Texas. I'm originally from Texas. I'm a fourth generation Texan, went to the University of Texas as well. And so I have a lot of experience working in the state of Texas. And as I go through these projects, these are all going to be slides like this. We're not going to have any graphs, no formulas, no techno speak other than to describe actual projects and concepts. So we're going to be talking about, you know, what are the advantages of precast, some of the design features, how that enhance these projects. And I'm going to try and again bring that into focus from a different type of delivery systems, typically being on the builder side. The way I've organized this is I'm going to go through substructure precast first, and then segue into superstructures, and I'm going to, you know, go through various projects trying to point out the features of how precast elements enhance the construction of these projects. And at the end of each section, I'm going to introduce some conceptual stuff that we're working on currently. So it's, you know, projects that we have experiences with that are actually built and in service, leading to, you know, how we're trying to advance bridge construction into the future with new concepts using precast concrete. First, I'm going to start out with your bread and butter, your basic workhorse substructure element, the multi-column bent with concrete cap. And on the right-hand side, there's an example of cast-in-place construction on shoring. I actually designed the shoring system for this particular project. As you can see, you've got to build a structure to build a structure. And that's really what cast-in-place construction many times boils down to. So you can see how you build a structure, you put a deck on it, you put forms up there, you're actually building a small factory on top of the structure, on top of the temporary structure that you have to take down when it's all said and done. And then on the left, can be set in a matter of minutes, and connections poured by the end of the shift, and in, you know, one day you've got the equivalent of something much more involved that's done with a cast in place. So really one of the big ideas that we've tried to develop in this is to make the connections easier. When you're casting a piece 200 miles away, shipping it to the site to set it on something that was cast in place with, you know, say number 11 bars protruding from it, there's not a whole lot of forgiveness. It has to fit. So to enhance the constructability of this, and constructability is really going to be my focus as I go through this thing, you know, constructability-based design. So how do you enhance the constructability? Well, you make sloppier connections, and I don't mean that in a derogatory fashion. I should probably say more forgiving connections. So it doesn't have to be perfectly aligned. When I first did these precast caps, we were sticking 8 to 12 number 11 bars out of the top of one of these columns, and then threading it down with 8 to 12 different post-tensioning ducts that were grouted using equipment that was specific to this connection, material specific to this connection. What we tried to do was use a corrugated metal pipe form that can just be filled with regular everyday deck concrete, typical job site concrete. And the only real refinement to that is we try to use small aggregate to get flowability in these more confined areas between the bottom of the cap and the top of the column. Here's an example right there in New Braunfels, Texas, the nexus of the universe of the Precast Manufacturers Association. This is out there on Loop 337 near Highway 46, near where I used to live. I lived in New Braunfels, just down the road from this place for about 3 years back in the 80s. So the idea is you bring in these precast caps, lift them off truck with a crane, and then you thread them down over these tight spirals of dowel reinforcing sticking out of the top of the column into these corrugated metal pipe forms. You set them down on shim stacks to get the grade where you want it, maintaining a 2 to 3 inch gap to get flowability of concrete. And then, as you can see, they have a sonotube form here to make the connection, the watertight connection between the bottom of the cap and the top of the column. And then you just pour good old regular concrete, vibrate it out through this thing. So it goes really very quick. Next example of this, further refinement, we actually precast these architectural capitals. These are basically sitting on a 0 length column, if you will. But as you can see, there's another example in the background of a similar type of construction. This was all cast in place. We were able to do all of this sort of fancy work in the precast yard, ship it to the site. And first element being the precast capital, you're able to do this sort of fancy forming in a precast yard. What we did was we made an 8 to 6 inch thick shell. The reinforcing from the column extended up into the shell, and then the dowels would protrude out. We would pour the plug here, if you will. You can see how that looks like in plan view. Here's some nice symmetric view. I mean, that looks kind of like Lego's instruction, if from my perspective. We've got a cast in place column. We set the capital on top of it, fill that full of concrete, dowels that go up into the precast cap that comes in, and that's really what it all looks like. We were actually able to bring drainage piping from the down through the capital and down to a clean out in the drain below. Here's a picture of what it looks like actually on the site. And this is, I think this is a really good photograph that demonstrates how all this really enhances the constructability of the project. You've got crew A that is setting these precast capitals, putting the plugs, setting temporary bearing pads down. Then you've got crew B coming behind, setting these precast caps and pouring the plugs. Crew C coming behind them, setting precast girders and deck panels, and then crew D coming behind, slabbing it out, putting the final deck on it. So you've got one operation marching in front of the other with prefabricated elements, making this go about as quickly as you could imagine. This project was really quite a success. Won some awards for design and construction. Going on to our next item of precast substructures, hammerhead cap is another real workhorse. Involves a little bit more design because you've got a transverse moments due to unbalanced loading or wind loads that have to be resisted. So there's a more structural demand on this type of connection. But we've come up with solutions through various different projects. This was being our first one. We had some really stringent architectural requirements for this, but there were quite a few bent caps on this job. So the specialized forms really made economic sense. We designed it, we left the design as a reinforced concrete cap and really just accommodated it with these same kind of connections that I'll be showing throughout the presentation. Haul weight was a bit of a problem. You got a 40-foot wide cap, weighs 120,000 pounds, so spreading it out on the various wheel loads was a little tricky, but they worked through those issues and got them to the job site. Here's a nice view of what this the void looks like. Now we did a 42-inch corrugated metal pipe on this 54-inch cap. We since were able to make these smaller and still have a design that meets all of the project design requirements. Here you can see where the plugs were poured. So you can set this guy, grade it out, and you can go up, do a little bit of trigger work, and then you're ready to pour the plug. Really very, very simple. You can get a cap built in a day. As a matter of fact, they built 6 in a day. As they got to their peak production on this thing, as they were setting them out, they were able to set 6 caps in one shift and pour the plugs. The 6 was really limited by the amount of trailers that they had to ship these caps to the job site. So as anything in precast, the limitations that you have are really bounded by what you can ship to the site. And I'll go through, you'll see that over and over again. You get too big, too heavy, then you can't haul it anymore. You have to break it up into pieces. The next hammerhead job that we did was on the Sergeant Beach project. It's really getting very close to completion of construction. They're doing final slabbing on that. But this one is a pretension cap, and as you can see, the corrugated metal pipe voids got a little bit smaller. We're still able to handle all the design loadings and have more concrete cover just for reinforcing protection, less congestion. These are pre-tension. You can see the strands extensions there before they've treated them on the edge. But the thing that really this picture shows me is the difference in finish between the precast element and the cast in place. These things came out painted, final finish on them, requiring really no further finish once they got to the job sites. And that's really another advantage that precast has, eliminating a lot of finish work on the job. These things were even heavier. They weighed 150,000 to 250,000 for these main span unit caps. We actually designed a haul trailer to spread the load out that we've used on other jobs as well, to handle these heavier loads and get enough wheels underneath them when you've got really something that's a lot shorter than, say, a long beam would be. This is what the caps look like. We've got three, the approach bents. We've got the transition bent at the expansion joints on the main span unit. We even had a precast back wall that we would place after we placed the basic cap. And then you've got your main span cap. Now these were 7 feet deep. These were 8 feet deep. Really look very shallow for carrying 12.5 foot deep girders, which I'll show you in a minute, supporting a 300-foot span. But we cast a diaphragm over the top of the pier at the center of the pier that acts compositely. So at the end of the day, you've got something approaching a 20-foot cap supporting those main span units. But really the appearance is that of this architectural lower cap. Going back to this again, 3-inch tolerance for placement, use regular hard rock concrete with small aggregates. One other advancement that we had on this was we eliminated all the bearings at the interior piers. We didn't really need them for movement, so we were able to put them on just Fabrica strips for erection on the approaches, relatively small 50-foot spans, and then cast a concrete connection at the interior piers. So really we only end up with expansion bearings at the expansion piers, either in the approach or on the main span unit. And again, there's no bearings on the main span pier as well. So moving back to New Braunfels, it seems like New Braunfels has a lot of going on as far as advancing precast construction. The San Antonio Street Bridge over the Comal River, I have intertubed underneath this bridge many times. It's just upstream of Schlitterbahn, and here's the outflow from the tube chute there in Landa Park. This project was a restoration and redecking of a 100-year-old, it's almost 100, it's more like 98-year-old bridge. Really very slender, elegant arches, very iconic bridge for the city of New Braunfels, and they wanted to maintain this historic look with the new project. And the way that they did that was they removed all of the framing that sat on top of these spandrel columns and the arches, and really left the arches and the spandrel columns behind as an architectural treatment, but they no longer support the bridge structure above. Really pretty clever. So you can see they started demolition here from the middle, working back to the ends, using this super heavy lift hydraulic crane. This was the key element in making this job go very quickly and smoothly in construction. They used it to lift off all the panels and decking from each end, then got down into the river bottom and set all these architectural frames and the slab beams up above. So they were able to get all of this done in one construction season, which really delighted the citizens of New Braunfels, because they rely an awful lot on the tourist trade at Schlitterbahn and the Comal River is very much a tourist attraction. So they were able to get all this done in the winter months, the fall and winter months when the river traffic was closed. So this is how they set these things. We brought in these precast frames. We sort of nicknamed them the pretzels. This replaced a diamond-shaped cast-in-place pier and cap type of basic design. And, at this point, I want to just, stop for a minute. This was a value engineering design, and everybody wanted to get this thing to go quickly, including the DOT, the contractor, the citizens of New Braunfels, and so we all worked together to come up with an idea that would use precast concrete to take the cast in place portion. Each one of these would have been cast in place, could have been very time consuming. We were able to come in and set these things in very short order and get them locked down to the arch. And everybody really had to work together because all of this is being done, all of this rework is being done in the construction schedule. So it really required a lot of cooperation and working together by all the stakeholders, being the precaster, the contractor, and the Texas DOT, and ourselves. So the delta frames, or the pretzels, if you will, are brought in. They're set over some pins that come out of this crook of the arch that were retrofitted in. There's reinforcing sticking out of each side that was cast into this block here to lock the frames in place. Then these slab beams are brought in that are supported at each of these frames, 70-foot span. And as you can see, these spandrel columns are no longer supporting it. The arch is really just there holding itself up and adding to the aesthetics of the final product. Went extremely well. Project was completed about 6 months ahead of schedule, with very little interference to the tourist traffic in there. And actually, the construction schedule for this project extends into this December. So it was intended to be wrapping up about now, and it was finished back in July. River traffic was open, and traffic was available to go over the bridge back in May. So well ahead of schedule. Really a total success that was really enhanced by using precast concrete elements. So I'm going to wrap up substructure presentation by segueing into a concept for Straddle Bench that we developed for a design build down in Houston. Idea wasn't used this time. It just didn't fit with the particular situation. But we really like the idea, and we've been looking at it on a number of different projects. And basically what it involves is using voided box beams, using the same side-by-side box beam technology that we have on a lot of our bridges. We're going to apply this to a straddle bent here. And we've developed designs for this up to 125 feet that can support bridges that are 60 feet wide, even with 200-foot spans. So you can, by combining a pre-tension box beam and a post-tensioning to finish it off, you're able to build these things in really relatively short order using precast concrete instead of either more conventional formed and shored or steel straddle bent. So it adds another option for this particular element. We were even able to add DAPs on for the section that's supporting the bridge above this, in this case. Other ones, beams can go up over the top as well. So this is how it goes together. You cast the piers, then you bring in the first beam and you set it down on the pier. You come in with the adjacent box beam and set it down. Those are braced off to the column. Then you cast the top slab and the shear key in between, as well as the column connections. And now you've got a uniform composite box beam system. You start setting the beams up above and the roadway below. But the compelling advantage here is that you've got some pre-manufactured elements you can bring in that takes care of the need for, that eliminates the need really for heavy shoring and interference with traffic below, and a lot of operations that could, impact public safety. So you can actually keep these roads open with periodic shifts to do erection here and maintain these facilities in a safe fashion and get the bridge built from up above with minimal disruption. So we think this is an idea that has huge promise going forward. So with that, I'm going to segue into superstructure construction, and I'm going to present on splice construction. I have a lot of experience with splice construction and 20 years. And this has become something that is over the last decade has become popular in longer span applications in Texas as well. This is really a pretty cool picture of the Phoenix airport, Sky Harbor Airport. This is an addition to the people mover system, and we actually dropped in spliced precast U-girders over a live airport terminal. It wasn't live when we set the beams, but as soon as these beams were set, they reopened this terminal, and there was a lot of foot traffic going through this bridge out to some various terminals where the airplanes were coming up really right next to the construction site. So I'm going to just briefly, for those of you who are not familiar with how spliced construction works, just go over the fundamentals of how all this comes together. As I stated before, it's all about getting big, heavy pieces to the construction site, and the less heavy and the less big they are, the better. You can break up longer span structures into a series of precast pieces with vertical supports. You can set them up at the job site and then cast in place small sections in between, post-tension it, make it a composite, fully continuous unit, and then pour deck slabs on it. We typically design these things to be supported, only the girders to be supported once it's all stitched together. And post-tension, we remove all that shoring and cast that deck in an unshored condition. One of the other advantages that we hope we never have to use is that we can replace the decks on these structures, that the deck slab itself is not essential to the load carrying of the bridge itself. So you've got a replaceable deck system that can be maintained for as long as you want with a durable, fully compressed post-tension structure, which has proven out to be really a very long-term durable type of structure. Here's a layout and plan view. We've designed these things in curved alignments as well as straight alignments. When you go to curve, we're typically talking about U-girder bridges. In straight, we can use either U-girders or bold T's that don't really have the torsional resistance that these U-girders do when they're closed up and make a closed cell box. So Texas has moved into this area. We've got 8 projects that are either under traffic or in construction right now. We've got 6 of these have been in service for a while and are performing very well. We've got Sergeant Beach is finishing up here. I expect it to open in a matter of a month or two, certainly early part of next year into this year. And the Grand Parkway Interchange in Houston, which is a curved spliced U-girder project, really a new technology being introduced that's really never been done before in Texas. But this Dart light rail bridge is a spliced bulb T bridge for the Dallas area rapid transit system, which has a 250-foot span over the levee in the Trinity River Basin, which was a new technology at the time. But we've just had a series of successes that have led us to continuing to build these kinds of bridges. And here's a lot of photos of the various ones. We've got one in Fort Worth. We got a number in Dallas, Seguin, Texas, Matagorda Bay. And they've been built in a whole lot of different delivery systems for a lot of different owners. So there's a broad type of technology. We've got one design build project that these have been built with, the Dallas Horseshoe, and 3 value engineering projects, the other 4 with your more traditional design bid build delivery system, but for a variety of owners. We've got 4 TxDOT bridges, 2 city bridges in Fort Worth and Dallas, and a couple owned by transit agencies, Dallas Area Rapid Transit and the Harris County Toll Road Association. First one was the Dallas Area Rapid Transit. As you can see, the levees here in Dallas are very touchy. They don't want any construction loads on them, so this had to be built to span over that particular levee for a branch of the Trinity River, a fairly small branch of the Trinity River. This is really more a matter of getting over the levee without disturbing it, because this is These things really do fill up with water when it rains. So 250-foot span, longest precast bridge built in Texas at the time. Really a groundbreaking project. And what the real significance to my mind, other than, this was a new type of project, was built successfully, was it introduced this type of precast shape, a new type of girder. This is 10 foot 10 inches deep and 82 inches deep at the shallow end where you go to the constant depth section. But what this did was it introduced a new product line into the state of Texas that has been used over and over again. This particular shape that was developed for the DART project has really been the workhorse for the majority of these spliced girder bridges that have been built in Texas. A lot of volume follows this one little 3-span bridge. And Sylvan Avenue was the next project built, and it was really a quite large application of this technology following on the Dallas area rapid transit project. This was a picture was taken in 2013 during construction. And this had three 3-span units, the largest being the river crossing over the Trinity at 250 feet. This is a 150-foot drop-in section with 98-foot long pier sections on either end. And following this one is a rather small bridge, an access road in Seguin, Texas, going over the Union Pacific Railroad. Couldn't get any construction equipment down in the site, so this was set up to be a zero impact to the railroad type of job. This was a value engineering proposal where we converted a 200-foot simple span to a 3-span continuous unit using existing shapes that formwork was available in the state, which greatly enhanced the economy of this project. But it also enhanced the constructability of it, I think. But what I wanted to demonstrate with these two slides is that these two projects are really sort of companions that show, this is a scalable solution. It can go from small bridges to much larger projects such as this. I mean, you got 10 to 12 girder lines, going hundreds and hundreds of feet. That was a lot of volume on that one, where this was a much smaller volume, but used the same solution. But what's really, I think, noteworthy on this particular project was because of the accelerated construction schedule on the Sylvan Avenue project, they wanted to set all of these girders continuously. Once they got their false work set up, they wanted to set them continuously until they were all set out, and then cast all of the splices, post-tension them all, and have a much more uniform, consistent construction operations. Well, what that meant is they had 62 splices to accommodate, and what that would require is 62 splices using a strong back system such as this, because the other two units had this drop-in section on the main span as well. So this is an example of a strong back unit that I actually designed here in Denver, Colorado, for a spliced U-girder bridge. But you can see this is you're hanging the adjacent girder from this heavy beam system that is lashed down to the girder that's cantilevering over the pier. Involved in terms of not only material supply design, but also fabrication, installation, and dismantle. And then when you're done with this, you got 62 of these puppies. What are you going to do with them later? You're basically going to scrap them all. So what we were able to do is work with the precaster to develop an embedded steel bracket system, which we've used on a number of projects since, and I'll keep featuring this, to actually bring in the girder that's to be supported from the one on the overhang, much similar to this, with an embedded steel tube system. These are, heavy wall structural tubing, roughly 12 inches deep, 4 inches wide, and we weld a little bearing plate on it. But this whole assembly costs, $100 to $200 a piece, where this costs $5,000 to $7,500 a piece to set up and dismantle. The other beauty of it is, there's no hanging bars to install or any of this kind of stuff. You just bring it in, set one on top of the other, and then we've got slotted holes on either side for dropping in erection bolts. Finger tighten them, and you can let go with a crane. On this one, the last girder that we set, we were able to do in about 20 minutes from the truck to dropping it off the hook, because this is really very straightforward type of way to support it. But you have to design all this for these heavy loads. And as you can see here on Sylvan Avenue, there's no external means of support. The other advantage is there's no dismantle. You just cast this thing and bury it in the splice, so you detail it to stay out of the way. So to give you an idea what this looks like in detail, I'm going to use the Seguin Bridge, which is the simpler bridge of the two. The pier girders here at section BB have the lower bracket, and this was actually attached to the end forms in the precast yard to hold it in place. Then the drop-in girder over here, section DD, that's the one to be supported. So you bring it in, and this one just sets right on top of the other. These are cast directly in the yard with it through the end bulkhead forms to make sure that they're in the right spot. And in this case, we erected the two end girders, cantilevered them roughly 15 feet over the end of the pier, brought this drop-in piece to make up the rest of the 200-foot span, everything done from the top. And all of this was erected in a 3-hour shift. So, you got 4 girders, we brought them in. All of this was done in between rail traffic, so there was no disruption to rail traffic. And I've done a number of these projects with railroad crossings in similar fashion with both strongbacks and these brackets. Railroads love them because we really don't have to have a traffic closure to be able to get these things set. And once these things are set, you're done. There's no, you form this up. You can do the vast majority of that work from the top. So again, very little disruption to the rail traffic. So this one went together very well. The contractor was very pleased with how that all slipped together. So taking all these ideas forward, Sergeant Beach Bridge is really the record setter here in the state of Texas. 300-foot span over the Intercoastal Waterway down near Matagorda Bay in Sergeant Beach, Texas. We've got larger beams here. These are 120 feet long, and they're 12.5 feet deep over the pier. In this case, you can see we had lifting winches that brought in this 180-foot drop-in girder. Similar in-span girders, 150 feet, I think, to 160 feet. We laid all this out during design to demonstrate, through a rendering, what the precast caps were going to look like, what the completed framing system was going to look like, because the aesthetic look of this was important to this particular district. And again, we've got a value engineering redesign, having to work in close cooperation with the precaster, the contractor, and the Texas Department of Transportation, both in the district level and at Bridge Division in Austin. And we worked through all of this sort of stuff. The basic design was 14 feet deep and really couldn't be shipped to the site from a land-based precast plant. So the challenge was, how do you design this thing with sufficient depth to handle a 300-foot span, but still be something you could ship over land? And that was how we were challenged to come up with this shape. We had done a couple of other proposals on projects, so we had some experience, and we knew that we could make a 12.5-foot deep girder work. Precaster said, if he can go to 12.5 feet, I can ship it there. And they went through really all of the various permutations that it took to get this thing approved, and all these things were delivered to the site. And this gives you an idea of the scale of the piece, even more, where we've got one of our engineers standing next to the piece in the precast yard in San Antonio. So this thing was shipped 200 miles from San Antonio, Texas to the coast. And this is a real game changer in my mind for the precast industry. This is something that can be used at any precast plant to get into the to take precast concrete into the long span arena. That's really been the purview of cast in place structures, segmental, or steel construction. Now we've got something where more conventional precast shapes can be cast without barge slip access, because the vast majority of these long span bulk T projects have been done on the coasts and cast in plants that had barges where they could cast a 15-foot deep piece and ship it to the site and erect it. And I'll show you, some other even longer span applications that we're working on that do require barge access. But in this case, we've opened up an opportunity to get up to even 325 feet with land-based precast, and I really see that as a very important development in advancing precast concrete. So once we got these cast, we started erection. We've already gone through the precast caps that we set. These are all precast slab beams on the approaches leading up to the main span unit going over the intercoastal waterway over here. So we started by setting the in-span units on a single tower of false work. Once those were all set out, we would set these pier girders. And I got a really nice, I guess, that we've really got some good photography on this particular project, because we really feel like it's a real groundbreaking type of project. So once these end girders are set, we're setting these pier girders with a single pick crane on the pier here. They're balanced, but in order to maintain stability and safety, we bolt these through some embedded steel brackets in the webs. So we actually bolt this end to the previously erected piece to keep it stable during construction, and then we'll make these splices on both sides, and then we'll start the main span erection. We've got a 180-foot deep long girder here that's 8 feet deep. It was a little too heavy and long, we thought, to ship, so we also had some issues with trying to maintain the vertical curve profile. So we broke this in half and site spliced it and actually cambered the girder to follow the vertical curve profile. Brought these out on barges and lifted them with a winch system, which really worked pretty smooth. This is my first experience really with a winch-based erection system, but this enabled us to not really have heavy cranes in the waterway on barges, minimize the disruption to the barge traffic as well. So once they're up there, as you can see, these are sitting on those same embedded steel brackets I've shown you on the other projects. We just keep rolling this forward. So this is a 180-foot girder that weighs 325,000 pounds sitting on those same type of steel brackets on the smaller projects with the 200, 250-foot spans. Once we get them all spliced, they were post-tension from the expansion joint end to the expansion joint end. False works removed, winches are taken away, and you've got a continuous girder line system that's ready for forming the deck slab. There's still on that. I tried to get some completed project photos, but we're just probably about a month too early to get there. So I'm going to real briefly touch on an exciting project in Houston, Texas, my hometown, 249 Grand Parkway project, which is in the early stages of construction. I'm showing you some pictures of the companion bridge, which is the J.T. Butler Expressway in Jacksonville, Florida. A very similar type of construction. We're using very similar details on this. We've designed both of these projects. This one is going to include 4 connector ramps on the south side of the interchange, the north side to be built at a later date, that are going to use spliced continuous precast U-girder sections. So a new shape being introduced into Texas. So this one's going to be a real game changer, I believe, as well. This is going to be 4th and 5th level connector distributors. So these guys are going to be way up in the air. And right now we're in the precasting section, stage of things, early in the project. We got site work, piers being cast, false work fabricated, and the beams being cast. So in 6 to 12 months, we'll have a lot more to show you on a project such as this. But this is the first application of curve precast in the state of Texas. So another advancement using precast concrete. Now, when we were practicing this thing a couple of days ago, Chris asked me what my favorite bridge project was, and without a doubt, this is my favorite bridge project. And forgive me if you've seen a presentation I've made before, but this job just has it all, and it's really a fairly small 3-span project. Nothing super daring, but it really typifies what you can do with precast concrete to really enhance constructability and economy on a project. This was built back in 2011, 2013. The bridge is being renamed for Rick Lawrence, who was the president of Lawrence Construction, was my client on this project. Rick passed away earlier this year, and he was a 4th-generation leader of Lawrence Construction, which has almost a 90-year history in the Denver area where we live. Rick was really quite an innovator, a professional engineer, and construction company president. And it was my client on this project. Rick really pushed the vast majority of these ideas that we developed on this project. And this was done as a value engineering proposal as well. And this really involved a lot of coordination between Colorado Department of Transportation, their bridge staff bridge group, ourselves, Precaster, and Lawrence Construction. The bridge that it replaced is what they call the Bronco Arches. It was sort of an iconic bridge, although it doesn't look that great from these photographs because it was pretty old and tired out by the time it was being looked at for either restoration or replacement. Rick Lawrence's grandfather was the head of Lawrence Construction that built the original Bronco Arch Bridge over the Platte River during the 50s construction of the interstate system. This is Interstate 25 that's carried over the Platte, which is not a overly impressive piece of river. There's drainage areas in Houston that are bigger than this one. So it's not a dramatic structure, but what really is important is this thing was carrying 200,000 cars a day. And this was a big problem on how to completely replace a bridge with 200,000 cars a day, maintaining all lanes during construction, and get this done in a very compressed time frame. And it was really built on a very compressed budget as well. 200,000 cars. This is the final product. It's a completely continuous, rigid frame, no bearings anywhere on this structure. We've got flexible abutments at each end. We've got a single drill shaft under each one of these columns. We've got about 40 feet of free length of the drill shaft before it hits the bedrock layer in a rather soft soil layer. So we've got a lot of foundation flexibility, enabled us to do this independent of any need for bearings. Very low maintenance project. As you can see, we've got the integral abutments at each end and a rigid connection between the precast beams and deck. But the real cool feature about this is a completely precast bridge. These are precast columns. These are precast beams. We've got a full depth precast deck up on top. Original design was very similar to this, so really it was a major tweak, I would say, rather than a scratch and redo. We had a solid cast in place pier here that Rick wanted to precast. He wanted to eliminate the bearings and just make a rigid connection. He'd built a similar project many years previous in Conifer, Colorado, had good success with that. We maintained the 6-foot pre-tensioned U-girder design with minor post-tensioning over these piers. That's really the only post-tensioning in this girder line, and I'll go into that a little bit more in just a minute here. Just really a very cool structure. It was initially conceived as a 5-phase construction, so we would, do demolition and add on the south end of the project, switch over to the north side, working our way into the middle. Rick was able to work with Colorado Department of Transportation to combine phases 2 and 3, get it down to 4 phases, accelerate the construction schedule. Again, we were working very close cooperation with the Colorado DOT through all of this. They designed the original bridge, and I worked with the design engineer through all the value engineering process, and really that close cooperation was essential to making this thing work. First thing we did was precast the piers. They wanted an arch look. The original pier was solid, so we were able to do these precast ribs with a connecting tie in between. These are some of the design details. We had reinforcing sticking out the top up into a void into the precast girder, so we cast a connecting diaphragm there. We've got reinforcing protruding out the bottom of the precast pier that overlaps with the drill shaft reinforcing, and I'll show you how all that went together. The girders were cast on a mud slab with FCO forms in the contractor's yard. We cast them on the job site because it's over 30 feet from here to here, so it was an interesting haul to get these moved the 300 yards from the storage site to the actual job site. We actually trucked them up an on-ramp and lifted them with a single crane with the lifting eyes incorporated into this cross strut. But they continuously cast these things and just stacked them up like cordwood until they were needed for construction. And this is how it went together. You know, you've got a little 12-inch footing is cast right on top of the drill shaft. FCO towers, conventional rental FCO towers built. The piers were threaded into these FCO towers, lined and graded. Connecting base was cast, so you could set these things on one side of the river, each side of the river in one shift, cast the base the next day. 3 days later, you're ready to set girders. So as I said, every phase, foundation construction, substructure, superstructure, decking, asphalt overlay, so forth and so on. So when I talk about a phase, it's all of these operations in each phase. So there was quite a bit to do to get this thing built, and by using as much precast as we could, we were able to accelerate this to really come in under the original schedule. So here we've got a footing poured that we're going to pour on top of the drill shaft. We're tying the cage for the connecting base. You bring in all of the piers in one shift. We threaded them on each side of the river in one shift. Poured the base the next day. That's what it looks like, threaded through the shoring tower. Cast the base the next day. 3 or 4 days later, you get strength and you're moving into girder construction. So you can see, again, like that job in Laredo that I showed you, one thing leads to another, to another, to another. And so you're in very quick order, you're moving through doing a lot of different operations in a very short amount of time. The design here of the piers was really based around the construction loadings. We designed these legs to support the girders, so there was no shoring required, no setup and dismantle on that. This is what it looks like when it's erected. And what was really there's just so many clever things that were done with this job. The precaster actually tied all of these anchor blocks and various diaphragm forming inside the box here at the job site, at the precast yard. So it was shipped to the site with the cages already tied inside the girders, which made it really very quick to set up and do all of these cast in place connections. So this is what it looks like after you've set it, the girder down on the column, the reinforcing protrudes up into the girder. We make a diaphragm casting on top of it, a thickening slab for negative moment capacity. Once that's done, you're post-tensioning these tendons just over the pier. And as I said before, this is a series of pre-tension beams that are clamped together through the splice over the pier, and that's all the post-tensioning that you have until you get into the deck. So once these are set, we're coming in with full depth, pre-tensioned 8-inch thick deck panels, pockets for shear reinforcing to connect it to the girders below. These were all set on leveling bolts, and it was lined and graded in about 3 days. Then all of the connecting concrete was cast. Now, what was really another cooperative effort on our part, the original specifications required sort of an exotic high-strength grout mix that had to be batched and pumped in on site. Each one of these flange lines has 15 yards, so it would have been very difficult to do that without cold joints. We worked with the DOT to allow us to use the same concrete as the precast panels, 7,000 pound mix to make that connection. These were all pumped in continuously. The joints were all cast, all in one continuous operation until all the connections were made. Then fairly light longitudinal post tensioning was applied with 4-strand tendons at about 3 to 4 feet on center. Membrane applied, overlay, striping, traffic shift, start again. So this gives you an idea of the chronology here. The first phase, we were bugging it out, took 164 days, got really good at it. The next phase, and this is everything. I mean, demolition all the way through to traffic shift, 104 days. And that's with 200,000 cars a day going through the traffic site. Excuse me. And with this maintenance of traffic plan that they had, really the motoring public really couldn't tell the project was under construction. Really, there was no disruption to any lane traffic during that period of time. Third phase, 102 days. And then the last phase that was wrapped up and completed in 121 days was actually a 2-week delay due to some heavy snow in late March, early April. But built ahead of schedule. And again, I'll stress it one more time, close cooperation. And, all of these value engineering projects that we've done require everybody to be on board with it and helping to move this along, because it's in the construction schedule where you're doing all this stuff. We were able to do all this, accelerated the process. We had really delay-free operations. Everything went together really very well. I don't recall a single issue that we had to solve that slowed construction down. And this was really based on an extensive use of precast concrete. So now at the end of the superstructure presentation, I'm going to go to some concepts that we're currently developing. This one's for a job in project in Cape May, New Jersey on the Atlantic coast. This is a shipping channel with 250-foot spans for boat traffic going inland from open ocean out here to the right. It's an S-curve shaped bridge, which we have preliminary designs developed for using spliced Girder Construction. But the thing that we're working on here is using a twin wall pier concept to connect these girders. You can set them directly on the pier with no shoring, make a connection, and then you've got sufficient capacity and rigidity to set these drop-in girders on either side, make a continuous structure with absolutely no shoring. And this is what it looks like when it's done, a super attractive structure, what we think is a very economical construction technique that is on the coast, very durable, corrosion resistant, construction-based design. And another exciting project that we're currently working on is two different projects, river crossings with 400-foot spans that use precast splice construction. And you can say, well, how the heck do you get a 400-foot span bridge built and shipped to the precast at a remote facility and shipped to the site? Well, the way that we do this, and this movie will kind of illustrate, we split the pier pieces in half and splice them over the pier. So we're breaking it into smaller and smaller pieces to be able to accommodate that. As you saw on Sergeant Beach, we did the drop-in by field splicing 2 pieces. But you're gonna ship as big as you can. But you see here we have the half pier piece set up on these what I call gigantic overhang brackets that are there just to keep that thing stable and supported until we can splice it together and connect it to these piers. So you bring in each half, set them all out, cast connecting splices, post-tension them together, then set the end spans, and then you're ready to set these drop-ins on the 400-foot span in the middle of the channel with barge-based construction. pier girders here about 15 to 16 feet deep. The constant depth about 9 feet deep. So as we get longer spans, we get deeper, heavier girders. But by breaking them in half, we're able to get something that you can actually ship to the site. We don't want to see that one again. So in wrapping this up, again, my passion in all of this is constructability-based designs. I get a lot of feedback from contractors on how to do things, what they like, what they don't like. And after 30 plus years of working with contractors, we try to focus on how you're going to build it before we do anything else, before we really run any numbers. It's got to be able to go together. It has to make sense in how you build it. And the way you do that is you use, simple repetitive details as much as you can. You give people greater tolerance at all the connections so you don't end up with feel problems. And this just tends to make things go smoother, which makes it go faster, reduces labor costs, less hair pulling and issues and rework, better finish on the product that you ship to the site. And also it can be done in a very efficient manner as well. So, restating what a lot of the advantages we have here, we've got reduced forming, we got a higher quality material, higher strength concretes, better quality control on the ground in the yard with established practices, improved safety by just removing a lot of intrusion on the job site. This is safety for the workers, safety for the motoring public, because you're reducing interference with traffic and reducing site operations. So with that, I'm going to wrap up that I'm bullish on precast concrete. It's what I do. It's my specialty. So we've come a long way with precast concrete. As you can see, we've still got a long way to go. But we've got really a high quality product that can greatly enhance the facility, the economy, and the scheduling of these construction sites and improve safety as well. So with that, I thank you for your time, and I'll entertain any questions you may have had.
Thank you, Greg, and thank you all for participating in today's program. I do have a couple of questions, and Greg has graciously agreed to stick around for a few minutes until we get these questions answered. I did want to clarify one thing, and that is the Texas Department of Transportation does not have what is traditionally noted as value engineering and instead uses contractor redesign. So keep that in mind as you may go through this presentation again. That said, the presentation will be available on precastcma.org. Greg, we do have a question, and it goes back earlier in the presentation regarding the caps. And what is wondered is if there is a rule of thumb on the length, weight, size, basically, of caps that can be used.
Sure, that's a good question. I'm not an expert on heavy haul, but so a lot of what I get is what I hear from the people I work for. What we've tried to do is keep these things as much as possible under 200,000 pounds. That was our initial focus. We've since grown beyond that. So in some of these longer span applications, heavier pieces like the ones in Houston, we've got shipping weights up to 325, 330,000 pounds. The splice girder that I showed you, that 12.5 foot deep piece, weighed over 300,000 pounds as well. So we've really had to work with a lot of local agencies. But people do heavy hauls all the time. I mean, I've done some load rating on bridges with transformers that were 800,000 pounds that were shipped here. So there's a lot of people out there with a lot of experience on this. But once you trip beyond the 200,000 pound, you're into the heavy, super heavy haul category, and then it gets tricky. So we try to keep it below that. A no permits 80,000 gross vehicle weight. So we trip that regularly, but we try to keep it below the super heavy, which is 200,000. Now, as far as lengths, I think the longest girders that have been done and shipped in Texas are 170, 180 feet. But traditionally, we're in that 120 foot range, which is everyday stuff. but it can be done, as long as you can figure out a way to do it. And that's really relies on the creativity and cooperation that you're going to get between public agencies and the trucking industry.
Thank you, Greg. And that actually brings up another thing that PCMA regularly offers consulting engineers as well as the Department of Transportation. And that is, can we get that section to the job site? And rest assured that the precasters will go out and run the route and make sure that they can get the larger size pieces to the job site for erection.
Yep, that's the thing. You can make it as big as you can make it, but you got to be able to get it to the job site.
And then finally, we have had a request for the handouts, and I was wondering if you could, if you mind if I do provide these, the presentation in handouts, keeping in mind, of course, that it will be available at precastcma.org.
Yeah, and in fact, I was able to embed that movie. The latest version of PowerPoint actually converts it to a smaller native file and sticks it in there, so it's completely transportable. So, yeah, you can certainly distribute that. It's about an 80 megabyte PowerPoint at this point in time, so it's a pretty big file. But yeah, you're certainly welcome to share that.
Very good, very good. And I believe that that's going to conclude our program for today. Should you have any questions that you think of afterwards, please feel free to contact solutions@precastcma.org. And we thank you for your participation in this webinar presented by Precast Concrete Manufacturers Association. Thank you.